Lovely to host you here every Wednesday of the month. Greetings, fellow leaders from the African continent and across the world. Welcome to today's live session. It's so lovely to have you with us. My name is Maud Nale. I am the communications lead here at Digital Earth Africa. And today we are going to be talking about a very interesting topic. Today's session will introduce soil data layers that have recently been made available on the Digital Earth Africa platform. The data comes from the iSDA Soil Initiative and supports Digital Earth Africa's mission to support food security and climate adaptation across the African continent. I'm so excited to be introducing today's presenter. He is a fellow colleague based all the way in Australia. He is the Senior Advisor for Capacity Development. Please join me in welcoming onto the virtual stage, Dr. Michael Wellington. Michael, you have been made a host. I see your video has been turned on. I'm going to hand the virtual stage over to you.
Thank you very much, Maud, and greetings everybody from Australia. As Maud introduced, I am a member of the Digital Earth Africa Global team based in Australia and employed by Geoscience Australia. I've been involved in Digital Earth Africa for several years now, and it's a great pleasure to meet with you all to discuss the new soils notebook that we've got available on the platform and the soils data more generally. So allow me to share my screen where you'll see the sandbox there, hopefully. Today, I will talk through the iSDA soil notebook, which is a datasets notebook, and also note that some of the data which we'll go through today is available on the Digital Earth Africa Maps portal as well. So for those of you who are familiar with the sandbox, you'll find the soil data notebook, iSDA soil, as you can see here in the datasets folder. So as Maud introduced, we have been fortunate to index and make available a range of soil data layers from the iSDA Soil Initiative. And we've been fortunate to collaborate with the good people at iSDA who are very professional and are quite similar in many ways to Digital Earth Africa in producing spatial information for the African continent. We've also noted through Joseph, Ken, Edward, Maud, and Rafilwe and the other capacity development team that have been involved in recent workshops across 6 African countries on food security, water security, and natural resource management, that we've received numerous queries for soil information to help support our work towards better supporting food security and water security in the African continent. So indexing soil data was a really logical step for us. Soil data has a range of applications. As we've just said, people are very interested in it for agricultural applications. One example of such an application is land suitability mapping for expansion of cropping areas or for development of irrigation infrastructure and possibly expansion of irrigated areas, and also for planning any amelioration or management of soil. So an example of that is using lime to overcome the constraints associated with acidic soils, or using fertilizer to address soil fertility. It's also important for planning construction or infrastructure. It's useful to know what kinds of soils are around the place where there might be housing or other developments planned. So I hope that's a useful background. I'll now step through the notebook cell by cell. It might get a little bit technical, so please stop me in the chat or otherwise if there's something you'd like me to clarify. But we'll go through. So the notebook demonstrates how we can bring the soil data in and integrate it with Digital Earth Africa products and workflows. There's a number of links provided in the background information and the description to the peer-reviewed publication on iSDA Soil, the iSDA Soil website, and also their GitHub account. So there's really only two main objectives of this particular notebook, and that's to load the soil data and visualize it against some existing Digital Earth Africa products and try and make some initial interpretations. So we start off as usual by loading all the packages, the software packages that we need to load the data and visualize it. Note here that we're bringing in a function from the DE Africa Tools suite of functions, or the DE Africa Tools package, and it's called Load iSDA. So that's a specialized function that's been created to bring in this data. We then connect to the data cube, and there's a description below that shows all 21 variables that are available as part of the iSDA suite of soil data layers. I note that there are 6 at this point. I'll go through this in more detail. There are 6 that have been indexed by Digital Earth Africa and are therefore available through the normal Open Data Cube loading procedures and on the Maps portal. But there is another way to bring in any of the other data layers, which we'll see in the notebook as well. So all of the data layers are listed out there. If you're familiar with soil science or geology maybe, or mineralogy or agricultural science, you might be familiar with some of these variables: effective cation exchange capacity, for example, total carbon, organic carbon, bulk density, depth to bedrock, pH, an important one, some nutritional or fertility layers, phosphorus, potassium, and nitrogen. They're the macronutrients that plants need to grow. Soil texture, sand, silt, and clay, stone as well. And then there's also a few additional layers available. So for each of those layers, there's an access name, which is the tag associated that we'll use when we load it up. And then for each variable, there are often several layers, and they generally relate to 2 depths. So the top depth, the most shallow, or the topsoil, I guess you could call it, 0 to 20 centimeters. And then there's a lower depth of 20 to 50 centimeters. And there's a mean and standard deviation for both those depths. So often, let's say for aluminium, extractable aluminium, for example, there'll be 2 depths, 0 to 20 and 20 to 50, and a mean and standard deviation for both those depths. So 4 layers in total. Thanks, Joseph, for linking that, linking the notebook on GitHub. So as I said, there are 6 layers that have been indexed directly by Digital Earth Africa. You can access all of the layers, but these are the ones that have been indexed. So that's bedrock depth, bulk density, total carbon for monitoring the carbon cycle, and sand, silt, and clay, so the soil texture layers. And then within each of those indexed layers, we can list out the measurements. So we call these measurements, but I guess they're separate layers in and of themselves. So as we said earlier, there's 2 depths, 0 to 20 and 20 to 50 centimeters, and also the mean and standard deviation. And within each of those, within the metadata for those measurements in the Open Data Cube, we've got the units. So for example, this is total soil carbon expressed in grams per kilogram, grams of carbon per kilo of soil. And there's a few other aspects of metadata listed there as well. Okay, so now we'll start off by loading some soil data for a coastal area near Cape Town in South Africa. So looking at the true color imagery here, we can see we're obviously on the coast. Looks like there's a bit of agriculture in this particular area in the central and southern parts of the region of interest. And then there's some sort of mountainous coastal country with some agriculture, but it doesn't look quite as fertile up in this part of the region of interest there. So in this case, we're interested in total soil carbon, and we'll get all 4 measurements, so both depths and both the mean and standard deviation. So we load that because it's indexed. We can use the normal DC load function, and that brings it in. Soil data is static, generally speaking, although of course it does change slowly over time. It's not like our satellite imagery where we get an image, let's say every 8 or 16 days. Soil data for the most part is static, so it's just indexed back to 2009, but we can apply it in any given time period, and we just have one timestamp there. So it's just a two-dimensional image, so to speak, or the time dimension only has one band. Importantly, many of the iSDA data layers do need to be transformed. So the way that they're stored means that they need a back transformation before they're in the units that we expect and we can start to use them. So that's quite important, because if we don't apply the transformation, we'll get nonsense numbers. So, we can see that there's quite big numbers here in this data set that we've just brought in, and we need to transform them before we start to visualize and analyze them. So fortunately for the indexed data sets, the transformation information is stored in the flags definition variable. So this line of code here shows you how you can access that back transformation. So in this case, for total soil carbon, we've just taken the data set, got the mean, and pulled out the flags definition. The back transformation is the exponent, the exponential of the data set divided by 10. So if we take that function there and we apply it to the data set, so we say our data set transformed is the numpy np dot exponent and the data set divided by 10, we can copy this function here and apply it. Then we've got our transformed data set. So now that we've conducted the transformation, we can make a plot. Once again, this is total soil carbon expressed in grams of carbon per kilo of soil. So we've got the range there, goes from roughly 0 up to over 60 for the mean in the 0 to 20 and the 20 to 50 layers. So I'm not sure if you can notice any kind of patterns there that you might associate with what we saw above. So it does look like there might be some higher soil carbon levels up here, whether that's because of the mineralogy there, I'm not too sure. And then the standard deviation, so the variation associated with that variable shown below. So that is the first step. That's loading iSDA data that's been indexed into Digital Earth Africa using the DC load function. And the next step that we'll show is loading the iSDA soils data from its source. So as we've written here in the notebook, there are 6 variables that are indexed and we can access them using DC load, and other data sets must be loaded from the source. There are some complexities associated with that method of loading, as we need to kind of set up a few functions and store some metadata for doing the back transformations and all this kind of thing. And we also need to apply a spatial projection to that data as it comes in. But this notebook, you shouldn't need to worry about that too much, because this notebook demonstrates how to do it. And again, thanks and recognition to the team at iSDA Soil who made some of this information available and assisted us in bringing this data onto the platform. So this cell here, the code cell, provides a link, and it sets up the variables and the different assets, for example, for Stack that are required to access the necessary metadata. So basically it's defining a few functions that we will use to load in the different iSDA soil layers. And there's no need to get too worried about the technicalities in there. The first data layer that we will investigate is the fertility capability classification variable, which personally is one of my favorites. I think it's pretty cool. So we can access that using FCC. So FCC is the tag, and hopefully it's written up the top here, so we can refer to it. Okay, we want our fertility capability classification, and the access name is FCC. So that's the reason we know to call our variable or VAR FCC. And then this is where we can use that function that we brought in earlier. So we can use the load iSDA function, give it the variable that we want, FCC, and then we're using the same region of interest that we defined above for South Africa. So we get the band data. It comes in slightly differently to what we're used to, but it's in X-array, so we know what we're looking at. We're pretty familiar with that format. We still need to apply the transformation. So all of the data or most of the data needs a transformation, and we need to check all of the data to see what transformation and whether it needs a transformation. So in this case, because we've used the load iSDA function, we can use the assets object that we stored to get the conversion metadata associated with each of the variables. So in this case, we've got our variable FCC, which we stored under the term VAR. And when we call the conversion, so we say we want the conversion, we go assets, FCC, extra fields back transformation. So the conversion is this particular function here. And then similarly, there's a demonstration here into the data set that we loaded. FCC has got to be what we loaded in originally, and then apply that function, the 3000. And then we've got our transformed data. We can also get labels from the metadata. So for the fertility capability classification, we see down below, we can kind of get a sneak peek at that figure there. That's a whole heap of different labels. So to bring them in, we get the FCC metadata and we map it back to our data set. So that this particular cell here just does that for us. And once we've done that, the next cell shows us how we can plot the fertility capability classification. So this variable is really helpful for planning agricultural expansion or planning agricultural land development or any kind of building or infrastructure development planning. I think this particular data is very helpful. So we can see it ranges up the top from quite a dark color where there are no constraints. So there's no fertility constraints. Basically, that means it's great soil, should be good for agriculture or any other similar applications. And then it goes from that dark color up through more kind of pink colors that we've applied into the really kind of bright colors where there's quite a lot of constraints. So the top one there is high erosion risk. There's textual contrast. So some part might be sandy and then there could be clay underneath it. It's calcareous, so that might mean there's a lot of limestone. Low potassium, so not very fertile, makes it harder for plants to grow. And high leaching potential, so that means that when it rains or when it's irrigated, it loses its fertility and nutrients a lot more easily. And then no data is where there's water, like we can see here for the ocean and for lakes. So if we take a look at this image here, we can see quite dark areas kind of around this central southern part of the region of interest. And over towards the coast, we can see much brighter colors. So they kind of match up to where there's slopes and mountains and hills are associated with higher erosion risk, of course. So when it rains, it's going to take more soil away with it. Lower potassium and high leaching potential. So the fertility capability is a bit lower. And if we scroll back up to the true color image, we can kind of see that sort of matches what we see with the true color. So we can see this kind of nice green area down in the central southern part of the region of interest, which is covered in, looks like reasonably productive agricultural land uses. And then if we head on over to some of the steeper parts, there's still agriculture, but it looks like it might be a bit more marginal. And it looks like the soil fertility might be a bit lower, as that plot below suggested. So that might be an interesting one to run for different regions of interest. So moving into some of the last examples, we can look at soil texture, in this case, clay content in the Okavango Delta in Botswana. So many of you will probably know that soil is comprised of 3 texture classes: sand, silt, and clay. The sand class has the largest particles, the silt's kind of in the middle, and clay has very fine particles. So clay is often very suitable for different agricultural purposes or growing grass and trees, because it tends to hold water and hold nutrients and fertility much better than sand, and sand has a much higher leaching potential, so the nutrients get lost from sand a lot more easily. So this, now that we're interested in clay content, we replace our VAR object and call it clay content. And then because it's kind of interesting to look at, in this case, we'll check out the part of the Okavango Delta in Botswana. See if we can observe any patterns. So once again, we use the load iSDA function to bring in the clay content, and it's expressed as a percentage. So VAR, which we've stored as clay, region of interest, the Okavango Delta, which we've applied above. And I should have said earlier, sorry, that load iSDA function will bring in all 4 layers, so the mean and the standard deviation at 0 to 20 centimeters and 20 to 50 centimeters, as we saw earlier. As always, we need to check if there is a transformation. In this case, there's actually no conversion, so that's blank when we run that cell. So there are a few layers where there is no transformation, but you need to check every layer just to make sure. And the data can be interpreted as a percentage, so we can proceed without any transformation required. So these plots once again show the clay content mean at 0 to 20 centimeters and mean at 20 to 50 centimeters, and the standard deviation as well. So just a quick visual interpretation, we can kind of see the brighter colors associated with higher clay content where the water is flowing in the delta, if we scroll back up to our true color image there. So we might conclude that there's deposition of clay that's happened over a long period of time as that water's flowed into those particular areas. So that has implications for, I guess, carbon storage and different natural processes that might be occurring in that particular system. So staying with the Okavango Delta region, I think the final variable that we'll load is pH. So we'll keep the Latin long definitions and just change the variable definition and leave it as pH. So once again, load iSDA function and bring in the data set. We can see straight away that, the pH, as we know from chemistry, generally ranges from 0 to 14, where numbers below 7 are acidic and numbers above 7 are basic or alkaline. So the fact that we've got numbers that are, 65, 73 should tell us that it's not quite ready yet. And so we do need to apply the transformation here. Always check. And in this case, the transformation is dividing by 10. So we just divide the data set by 10. That's our transformation. And it takes our data set from 60 to 70 back to, more familiar values for pH around 6, 7, that kind of thing. So then we plot out the pH. We can see here 0 to 20 and 20 to 50 centimeters depth. So notice as well that the range is a little bit different. So at 0 to 20 centimeters, the range is a little bit more acidic. So it's a lower range. It starts closer to 5.5. And the range is slightly bigger at 20 to 50 as well. So it goes up to over 8, whereas we only kind of go up to just nudging 8 at the surface. So we can play around with that if we want to do a proper comparison between depth layers. But we can see that, this darker area up here where the pH is lower, that's potentially getting slightly acidic. So it's below 7. It's somewhere, it looks like around 6 or even down at 5.5. So if we scroll back up to the true color image of the delta there, that's, I guess, kind of that stony area that's a bit lighter in color, I think. So it just goes to show that there's perhaps a little bit less regulation of pH and buffering capacity there maybe. So, sorry, that's the clay. So it looks like we've got slightly better pHs in these brighter areas, a bit more closer to 7 and even getting over 7, which might be getting a little bit alkaline. So that's all the variables that will load in this particular notebook. So to recap again, there are 6 that are available using the DC load function. And we started off with the total carbon example in South Africa. So that total carbon is loaded using DC load, and the transformation is applied. So you can access any of texture or carbon layers using DC load. For the remainder of the layers, we used the load iSDA function. So that's loading iSDA data from source. And for each of those, and including the ones that are indexed in Digital Earth Africa, we have to apply a transformation. So the fertility capability classification, the clay content, and the pH. So hopefully that's been interesting and helpful and useful for you in terms of giving you an introduction to loading and visualizing the iSDA soil data in the Digital Earth Africa sandbox environment. There's a couple of questions there about the Okavango delta and clay and pH patterns that we've discussed a little bit already, and also the fertility capability classifications. So you might like to try loading data for other areas or even loading other soil variables and seeing what you can find and seeing what you think. But I might leave it there for now, Maud, and hand back to you and welcome any further discussion.
Thank you so much to you, Michael, for this presentation. Very technical subject indeed, but I'm very certain that the leaders who need to get this information do understand exactly what was being said. In the chat box, we'll also drop this in the comment section. It's github.com/Digital Earth Africa. In the sandbox notebook, we're going to put that particular iSDA data set for you to give you an opportunity, leaders, to connect with us. I think that's really important as we grow this community. And now on the screen, I've shared the different ways that you can do so through our website, which is www.digitalearthafrica.org. You can also email us, info@digitalearthafrica.org. I also just want to speak about some online courses that we have available. They are free, self-paced. You can do it at your own time and pace, and you'll receive a certificate of completion at the end. If you're keen to know a bit more about those particular courses, you can log on to learn.digitalearthafrica.org. And we're also on social media, Twitter, LinkedIn, as well as YouTube, by the same name, Digital Earth Africa. It's always so lovely to have you with us, leaders, every Wednesday. Thank you so much for your time. It has become customary for us to take a picture for our social media pages. So I'm just going to first thank everyone for joining us, for your participation. If you speak French, we'll definitely meet again next week. It's not going to be this particular live session, but we'll definitely be one in French. And then we'll make announcements in coming days with regards to this live session that we've hosted today, when we are going to have it in French. But until we meet again, please take care and be safe, and have a good morning, a good afternoon, a good evening, and a good night, depending on where you're joining us from.